Golden Iris Productions presents Our Universe. Chapter 1. How the Universe Began. Ancient Beliefs and the Expanding Universe. For centuries in the Western world, many Christian Europeans believed the Earth was only a few thousand years old. Based on biblical interpretations, they imagined a world created in 7 days, fixed and unchanging. Geology and anthropology revealed a very different story. Rock layers, fossils, and radiometric dating show that Earth is billions of years old, opening the door to a deeper question: how old is the universe itself? The Big Bang. Astronomers discovered that distant galaxies are moving away from us. The universe is expanding, meaning it must have been smaller in the past. Scientists propose that the universe began as an unimaginably small, hot, dense point called a singularity. From this state, space itself expanded outward. The Big Bang wasn't an explosion in space, it was the expansion of space itself. The universe appeared everywhere at once, like mist forming across a cool field.
A universe of pure energy. In the first instant, temperatures were so extreme that matter couldn't exist. Only pure energy filled the newborn universe. The primordial plasma. As the universe expanded and cooled, energy condensed into quarks and electrons. These formed a hot plasma so dense that light couldn't travel through it. Within the first second, quarks slowed enough to bind together into the first protons and neutrons. A few minutes later, the universe cooled enough for protons and neutrons to fuse into hydrogen and helium nuclei. The first atoms. For hundreds of thousands of years, the universe remained a glowing plasma. Electrons were too energetic to bind to nuclei. Around 380,000 years after the Big Bang, electrons finally bound to nuclei. The first stable atoms formed, and the universe became transparent to light.
The Dark Ages. With atoms stable, the universe entered a long, dark era. No stars existed yet, only vast clouds of hydrogen and helium. Small variations in density became seeds for future structure. Gravity amplified these ripples over millions of years. Gravity takes over. Hydrogen gathered into denser clouds. Gravity pulled them inward, compressing them under their own weight. As clouds collapsed, their centers heated dramatically, reaching temperatures needed for something extraordinary. The first stars ignite. When collapsing cores became hot enough, hydrogen fused into helium. The first stars burst into light. Inside these massive early stars, fusion created heavier elements: carbon, oxygen, and beyond.
Supernovae and element creation. The earliest stars were huge and burned quickly. When they ran out of fuel, they exploded as supernovae. Supernovae forged heavier elements, iron, gold, uranium, and scattered them across the cosmos. Galaxies and planets begin to form. Matter continued to clump together. Stars gathered into spirals, clusters, and cosmic webs. Around young stars, swirling disks of dust and gas condensed into planets, moons, and asteroids. Building the first stars. The universe had taken its first great steps, from pure energy to stars, galaxies, and the elements of life. Next, we will continue with how the universe built the first stars, elements, and worlds. To be continued.
Golden Iris Productions presents Chapter 2. How the Universe Built the First Stars, Elements, and Worlds. How gravity pulled hydrogen together. Gravity acted slowly but relentlessly, gathering hydrogen into enormous clouds. Over millions of years, these clouds grew denser and hotter.
As the clouds collapsed, they formed vast stellar nurseries filled with swirling gas, the birthplaces of new stars. How the first stars ignited. When the core of a collapsing cloud reached about 10 million degrees, hydrogen atoms fused into helium, releasing enormous energy. Fusion pressure pushed back against gravity. The first stable stars formed, shining brightly across the universe. How stars forged heavier elements. Inside stars, fusion continued building heavier elements. Small stars created carbon and oxygen. Massive stars forged silicon and iron. These elements would one day form planets, oceans, atmospheres, and life. Stars were the universe's first great creators.
How supernovae spread the elements. When massive stars exhausted their fuel, their cores collapsed. The resulting supernova explosion blasted newly formed elements into space. These scattered elements mixed with hydrogen and helium, enriching the galaxy with the materials needed for future solar systems. How galaxies and planets formed. Gravity pulled stars into spirals and clusters. Over billions of years, galaxies collided, merged, and reshaped themselves. Around young stars, disks of dust and gas slowly condensed into planets, rocky worlds, gas giants, and icy moons. Our own galaxy, the Milky Way, formed through the same process. Billions of stars, including our Sun, would eventually call it home. Gravity sculpted the cosmos, gathering stars into spirals, forging elements in stellar hearts, and scattering them across space. From this cosmic alchemy came the raw materials of planets, moons, oceans, and eventually life itself. Next we will explore From Clouds to Solar Systems. To be continued.
Golden Iris Productions presents Chapter 3, The Birth of Solar Systems and the Rise of Worlds. From Clouds to Solar Systems. Across the galaxy, enormous clouds of gas and dust drifted through space. When gravity overcame their internal pressure, these clouds collapsed inward, forming dense, spinning regions called protostellar nebulae, the birthplaces of new stars. As the cloud collapsed, conservation of angular momentum caused it to spin faster and flatten into a disk. At the center, material piled up into a growing protostar. Around it, the remaining dust and gas formed a wide, rotating protoplanetary disk, the foundation of future planets. When the core of the protostar grew hot enough, nuclear fusion ignited. A new star was born. But the surrounding disk remained in orbit, slowly cooling, clumping, and beginning the long process of building worlds. How dust grains become planets. Inside the protoplanetary disk, tiny grains of dust collided gently. Electrostatic forces caused these grains to cling together, forming larger clumps called pebbles. As pebbles drifted through the disk, they collided and merged. Some stuck together, others shattered. Over time, the winners grew, forming boulders, then kilometer-sized planetesimals. Once planetesimals became large enough, gravity became the dominant force. They pulled in nearby material, sweeping up dust, pebbles, and smaller bodies. This runaway growth created protoplanets, the seeds of future worlds. Why some worlds become rocky and others become giants. Close to the young star, temperatures were scorching, too hot for ices or volatile gases to survive. Only metals and silicates could condense here, forming the seeds of rocky planets. Farther out, the disk was cold enough for ices to freeze, allowing bodies to grow much larger, the first step toward gas giants. A critical boundary formed in every young solar system, the frost line. Inside it, only rock and metal could solidify. Outside it, water ice, methane ice, and ammonia ice accumulated. This boundary created two families of planets, rocky worlds and gas giants. Beyond the frost line, icy planetesimals grew rapidly. Once they reached several Earth masses, their gravity pulled in vast amounts of hydrogen and helium. This runaway gas capture created the gas giants.
enormous worlds with thick atmospheres and small rocky icy cores. The violent early years of planet formation. The early solar system was chaotic. Protoplanets and planetesimals collided constantly. Some merged into larger bodies, others shattered into debris. These collisions shaped the size and composition of young worlds. Some collisions were so massive they changed planets forever. A Mars-sized body struck early Earth, creating the debris that formed the Moon. Other impacts stripped Mercury's outer layers and tilted Uranus on its side. For hundreds of millions of years, leftover debris rained down on young planets. Asteroids and comets delivered water, carbon compounds, and other essential ingredients, shaping atmospheres, oceans, and early habitability. From collapsing clouds to spinning disks, from dust grains to planets, the universe transformed into a landscape of solar systems. Collisions forged moons, bombardments delivered water and carbon, and gravity sculpted the architecture of young worlds. By the end of this era, the cosmos was filled with planets, each with its own story and potential. Now that the universe has taken shape on cosmic scales, we now turn to trying to understand how this universe formed. Next, we will learn how gravity was discovered and how we came to understand what we know today. The story of gravity. To be continued.
Golden Iris Productions presents Chapter 4: The Story of Gravity. How we discovered the rules of the cosmos. How we came to understand gravity. Early Greek philosophers imagined a universe of perfect circles and natural places. Aristotle taught that Earth sat unmoving at the center, and objects fell because they sought their proper place. Gravity was not yet a force, it was a tendency. Ptolemy refined the Greek worldview with a mathematical model of epicycles. Planets moved in circles upon circles, all centered on Earth. This system dominated for nearly 1,500 years. In the 1500s, Copernicus proposed a heliocentric cosmos. Earth became a planet, and retrograde motion became geometry, not mystery. A simpler universe emerged, but the forces behind motion were still unknown. Using Tycho Brahe's precise observations, Kepler uncovered 3 laws: elliptical orbits, equal areas in equal times, and a precise relation between orbital period and distance. He revealed the hidden mathematics of the solar system. Galileo showed that falling bodies accelerate equally, and that motion continues unless acted upon. He shattered Aristotelian physics and linked terrestrial and celestial motion. The stage was set for a universal law. Newton united the cosmos with a single idea. Every mass attracts every other mass with a predictable force. The same gravity that pulls an apple downward keeps the moon in orbit. For the first time, the universe ran on universal laws.
When classical physics reaches its limits. Newton's laws explained planets, tides, comets, and falling objects, but they could not explain the orbit of Mercury, the nature of light, the structure of atoms. A deeper layer of reality was waiting. At the turn of the 20th century, strange clues emerged. Atoms emitted light in discrete colors. Energy behaved in packets. Electrons acted like waves. The classical world began to crack. The rules beneath reality. Max Planck discovered that energy is not continuous, but comes in tiny packets called quanta. This idea launched quantum physics, a new language for nature. Light behaves like a wave and a particle. Electrons do too. Reality at small scales refuses to fit classical categories. Heisenberg showed that certain pairs of properties, like position and momentum, cannot both be known precisely. Quantum physics deals not in certainties, but probabilities. Modern physics describes particles as excitations of underlying fields. The vacuum is not empty, it seethes with energy and possibility. This is the foundation of the early universe. To understand the first moments of the universe, we must understand the rules of the quantum world. Gravity sculpts the large-scale cosmos, but quantum physics governed its birth. The deepest layer of reality lies in the quantum fields that built everything we see. But before we can explore quantum gravity, we must first understand gravity itself. So we step back more than 3 centuries to Sir Isaac Newton and the moment gravity first became a science. To be continued.